Now we will learn about busy waiting concept, types of semaphores like counting semaphore and binary semaphore. So last session we have seen about the semaphore concept, where semaphore is a control variable or integer variable. The default value is equal to 1, and whenever you go for a wait function, it decrements by 1, and whenever you go for signal function, it increments by 1. So the wait function and signal functions are completely atomic. No preemptions are allowed. So every process is supposed to have two functions to use to access a critical section. That is a wait followed by critical section followed by signal section. So I have shown some examples. Something like wait of S. If at all the S value is equal to 1, you can successfully decrement so that you can enter into critical section. While going out of critical section, you have to use a concept of signal of S. Then the signal function is going to increment the value. Then automatically S becomes 1 once again. It resets to 1. So what is a wait function? Wait function is having a small condition, that is, if S dot value lesser than is equal to 0. If S dot value lesser than is equal to 0, then what is the concept is whether is it possible to have successful wait or unsuccessful wait. If S dot value less than is equal to 0, then it is going to be what? Unsuccessful wait, because the particular process may be entering into sleep state. So you can decrement using S minus minus if the condition becomes fails. The meaning of S minus minus is nothing but the S value can be decremented by 1 using this. In the same way, the other function by name called signal of S, where you are having only one statement, that is S plus plus. So that means the decremented value becomes incremented with 1. So this is the small idea about two atomic functions which are completely controlled by your semaphore. That is nothing but Dijkstra variable, you may also call it as. Now, let us see few of the examples on semaphores. Wait mutex. So here the mutex, when we say that it is nothing but mutual exclusion, you can also call it as a semaphore, because semaphore guarantees mutual exclusion and progress. If at all n number of processes are there, very long processes, then bounded waiting may not guarantee. But few processes, if are listed earlier, or if we notice, then we can say that their bounded waiting also possible. So semaphore guarantees mutual exclusion as well as progress as well as bounded waiting. So according to this, semaphore value initially is equal to 1. Here mutex, when I am saying mutual exclusion, that's the meaning of it. It is 1. I am using a wait function, then 1 becomes a 0. Then you are successfully entering to a statement that is called, it is printing a 1. It is printing a 1. Then after that signal of mutex, then 0 becomes a 1. That's it, process P completed. Then process Q in the same way, wait mutex, 1 becomes 0. Then it prints 0. Then signal mutex, 0 and 1. Then the process Q is responsible for printing zeros. Process P is responsible for printing ones. As many times you are executing process P, it is giving you ones. As many times you are executing Q, it is giving you zeros. So this is one way if you are executing the process serially, P after Q, then the result will be what? Ones followed by zeros. Q after P, the result is nothing but zeros followed by ones. But here, the mandatory condition is they are executing parallelly. The meaning of execution of parallelly is nothing but preemptions are allowed. So what does that mean by preemption? Let me execute in a nice manner. Let us say process P started. When process P started, it is making mutex. What is the mutex value? So 1 becomes a 0. Then immediately there is a preemption. The preemption is saying that process Q would like to access. When Q is accessing, which is nothing but, it is also cross-checking weight of mutex, but already mutex value becomes a 0, then you are going to be under what? Wait. You can't take it because already some process is in the critical section. Here, the important thing is that I have not mentioned a concept of a critical section over here. Just I am saying only print 1 and print 2. Now, if you look at the concept, if at all the process Q has given a preemption here, then in this case, it is also same story. Already this 1 becomes 0. Now 0, this guy is going to be under what? Waiting state. So Q cannot enter unless process P finishes. Then reverse. So after that print 1 is completed, then I say signal of mutex, then this guy come into the picture and execute it. This is one way. If at all process Q is initiated, if at all process Q is initiated, it just performed wait of mutex, then 1 becomes 0. Then if at all this guy given a preemption here, so his wait condition becomes fail, it becomes a -1. Then here also, what is the result? It may execute 0 followed by 1s. But he said that very clearly, if process PQ executes concurrently, that means parallelly, and what is generated string by the above, sometime process P is executing and process not is coming. Sometime process not is coming, that means process Q is coming, sometime process P is coming. Either it print continuous zeros or it may print continuous ones. That's an idea. Let us see another example. This time, very strictly asking if they are executing serially in the way P executes, after that Q executes. P executes means same. 1 becomes 0, it prints 1, then signal. That means 0 becomes 1. Then what is the value it is printed? 1. Then after that Q is executing. When Q is executing, again 1 becomes 0, then it's printing zeros. So what is the meaning of that? P followed by Q, P followed by Q, it is following a pattern which is nothing but 1 0 star. So that is your answer. If you run parallelly, as it is not following the concept of any process synchronization, then there may be a chance of what anywhere to anywhere preemptions can give, then it may execute 1 or 0 stars. And the next one is semaphore with busy waiting concept. What is a busy waiting? Let us say there is one trial room. There is a one trial room and persons are trying to enter into it, especially process X. He has arrived first. He entered into the trial room. That means what he might have performed? He performed wait of semaphore. Let us say it is controlled by semaphore S. So now process X is inside. Okay. Then process Y is also wants to enter into critical section, which is nothing but trial room, as it is a shared resource. As it is shared resource. Now Py cannot get a chance because his wait is getting to be unsuccessful. Here his wait is successful because 1 becomes 0. His wait is unsuccessful because s dot value is not greater than 0. Therefore, this is going to be unsuccessful wait. When it is unsuccessful wait, then the particular process Y is supposed to be under waiting, because it indicates that when you are unsuccessful, it indicates that somebody is already inside. Or when a process, the semaphore value is 1 becomes 0, it indicates that somebody is already inside. Only 3 terms. 0 means critical section is busy. 1 means one process can go inside. One process can go into critical section. And process 2 means, so semaphore value is 2, so 2 process can go into critical section. So in this case, he is under waiting. Now, what is the busy waiting concept? Every time he is taking a so long. So every time he is cross-checking the condition whether is it free or not. It is replying that he is busy. Again, I am knocking the door. I am knocking. Is it available? Is it available? That means you are wasting the CPU resources for checking a condition whether critical section is freely available or not. This is the solution called busy waiting. So what is the concept of busy waiting? Busy waiting is a process is under waiting without doing any fruitful work. It is busy for some resource, but that resource is already locked by other processes. Then you are waiting for that particular resource without doing any fruitful action. This is what is the meaning of busy waiting. I am busy at the door, but door is inside locked. I will wait as long as the door is unlocked. So this is the way. As many times he is unable to come, those many number of times I keep on checking, are you free, or are you free, or are you free or not. So that's the concept of busy waiting. Then other side he will say that please wait, I am inside. Please wait, I am inside. So here the wait S is under what? Busy wait. That means you're trying to check whether the particular resource available or not, but that resource is not available because it's already locked, and you're trying to, every time, are you available or not. This is what is a concept called spin locks. Spin locks. You're going and checking, coming back. You're going and checking and coming back. So without doing any fruitful action, you're waiting for that particular resource. So what is a busy waiting? A waiting technique in which a process repeatedly checks a condition while consuming CPU cycles. Because you are wasting CPU for the validation checking, is it free, available or not. And this busy waiting can be implemented a concept called a spin lock, a locking mechanism that implements a busy waiting concept. So since the process remains active while waiting, it wastes CPU cycles without performing any productive task. So this is a very pathetic situation according to operating system concern, because a particular process supposed not to wait for a particular resource and somebody is inside. So why are you keeping the particular process in active mode? You tell the process to sleep. Again, I'm repeating, you tell the particular waiting process to sleep. Don't consume CPU cycles and memory cycles. Better you pause yourself. Then operating system will wake up. Whenever the particular resource is available, for example, trial room, the guy is unlocked and the guy is responsible, and the operating system is responsible to say that whoever the sleepy processes are there, that process will be a wake up. So the busy waiting concept can be avoided, because the meaning of busy waiting is wastage of resources only. because you are not doing anything but you are waiting. So why are you waiting? Better to relax. Don't use any CPU cycles. And whenever the particular process, a critical section is completed, then operating system will wake up you. So here, two important system calls we are using. One is sleep, the other one wake up. Sleep in the sense, when you know that somebody is already inside the critical section, you better to sleep. And when the particular resource is available, then operating system will give you wake up call. So the order of the processes which are in the sleeping stage, based upon the order, the particular wake up call will be given. So let us see a small example here. So there is a resource X which are trying by different processes like P0 and P1 and P2, one more P3, and RX is under shared mode. RX is under shared mode. Therefore, everybody can able to access RX, but that based upon order. Whoever first request for RX, if that RX is freely available, then his wait is going to be successful. So first P0 is checking, I want to go for RX. Luckily, RX is not at all allocated to anybody else. Then it is given a grant. After some time, P1 is trying for wait of yes. Then it says that not possible. Not possible because somebody is already inside the RX. Then this wait S, don't wait. Don't be under waiting because your CPU cycles are getting to be wasted. Then immediately better you give a what? Sleep system call. So you will be paused till that RX is available. After some time, P2 also tried for the same. Then he is also kept under waiting because RX is busy with P0. Then operating system also issues a sleep system call for him. Then after some time, P3 is asking wait function. Here also wait of S is unsuccessful. Then he will also be under what? Waiting. And operating system will give you what? Sleep system call. This is how you can avoid the concept of busy waiting. What is a busy waiting? You're waiting without doing any action. But in this case, you are not waiting, you're sleeping. Because you have been given a sleep system call, so you relax, don't, you're not accommodated any kind of resources because you're under sleep. When these guys are wake up, as long as after some time, P0 releases RX. Then while he is going, he will usually go for signal of yes. When signal of S come, wait of S make your value to 0. And whenever you give signal of X, then 0 becomes 1. That's it. The OS will give you wake up call. To whom he is going to give wake up call? Whoever is waiting for the first, he will get the wake up call first. Then after that, second, he will get the wake up call. Then after that, he will get a wake up call. When this guy and this guy will get a wake up call soon after completion of P1. Right now, P1 is given a wake up call. So this is how you can send the process to sleep state. Therefore, their CPU cycles are not get to be wasted. This is what is the solution of busy waiting. So busy waiting is nothing is but it is one of the dangerous situations for the process concept because the process is waiting for the critical section, though critical section is not empty, which is already allocated to previous process. And that waiting we will make into non-wait by issuing a sleep system call. So that is a solution for busy waiting problem. So the busy waiting problem can eliminate by modifying semaphore structure. How? Because I am adding a sleep state concept. Therefore, you're supposed to add one more column to your semaphore called sleep. Sleep is nothing but suspend. So earlier semaphore structure has only one value, that is integer value. Now you have taken a one more value, that is nothing but suspended processes. According to the previous example, when I say that semaphore is equal to one initial value, When P1 is requested, then immediately wait of S is successful. Yes, it is successful wait. Then he is entered into the critical section. After some time, P1 has come and P1 is also trying for wait of yes, because there is a rule to access a critical section. First you need to go for wait, after that you need to go for signal. Then this wait is going to be what? Unsuccessful. Why it is unsuccessful? Because already semaphore value is equal to 0. You have to underwait. It is known as unsuccessful wait. Then instead of waiting, what it is issuing? It is suspending. Suspend P1, then issue sleep system call. So you are out of the race. Therefore, who is benefited? Here, who is benefited? P1 is only benefited because its CPU cycles are getting wasted because of waiting unnecessarily. Better you come after some time. Which time? OS will tell you at what time you're supposed to come. Then some time, soon after some time, then process not completed its execution, and as usually according to the rules, it has to give signal of yes. Then 0 becomes 1. This time, the OS will give a wake up call to P1. So, wake up call to P1, then it is saying that wake up process P1, then his wait is getting to be what? Successful. And weight of S1 becomes 0 because this one value, the semaphore value becomes 1 now. Then you can utilize what? Critical section. That's why two particular rows is supposed to maintain. One is for integer value and the other one list of the processes which are under suspended. So your new semaphore structure, it is a record which consists of value as an integer and L is a list of suspended processes. So here you are having a semaphore value. Here you are having a semaphore value and whether it is suspended or not. So this is a list of the suspended process. This is your semaphore value. So s dot value is nothing but semaphore dot value. Value is accessed. S dot list is nothing but list of the processes are accessed. So this kind of structure who is going to follow? Like adding a suspended list to the semaphore. Nothing but modifying the semaphore structure is done by two different varieties of semaphores. They are none other counting semaphore and binary semaphore. So what is a counting semaphore? It's a semaphore value can be decremented, the value can be incremented, the value can be nullified. I will say counting semaphore. Count is nothing but the count can be decremented, can be incremented. Let s is equal to 1. Then when I say that weight of s, then s becomes a 0. When you say weight of s, then s value becomes 1, becomes a 0. Then this is from P0. When P1 comes, when I'm saying weight of yes, then 0 becomes a -1. Because this is a counting semaphore, not like ordinary semaphore. Ordinary semaphore, you are having the concept of what? Busy waiting. Now semaphore structure is modified. Now there is a P2. Again, I say that weight of yes, yes. It is unsuccessful only. Please agree. It is unsuccessful down. But you are making it down, down, down. What is the meaning of 0? When I say 0, critical section is busy. What is the meaning of -1? One process is suspended. One process is suspended. That is the meaning of negative value. What is the meaning of -2? The -2 say that two processes suspended. Two processes suspend. This is how you will come to know that how many processes are active and how many processes are in suspended mode. By seeing semaphore value, you are in a position to say that how many are in suspended and how many are not suspended. One more example with a counting semaphore. I say counting semaphore s is equal to 9. What is the meaning of 9? 9 successful downs. Remember, 9 successful downs. Down is nothing but weight function. Weight is nothing but P function. 9 successful downs. Process not. Yes. Weight of yes. 9 becomes 8. Then process 1. Weight of yes. 8 becomes 7. Process 2. Weight of yes. Then 7 becomes 6. Then process P3. Weight of yes. 6 becomes 5. Process 4. Weight of yes. 5 becomes 4. Process 5. Weight of yes. 4 becomes 3. Process 6. Weight of yes. 3 becomes 2. Process 7. Weight of yes. Then 2 becomes 1. Process 8. Weight of yes. Observe. This is the last statement. This is 1 becomes 0. What is the meaning? The positive value 9 indicates 9 processes can be at a time into the critical section. 9 processes can be at a time into the critical section. So the problem with the counting semaphore is excellently it works, but because of this, it is violating mutual exclusion property. What a mutual exclusion is saying, at a given instance of time, only one process is allowed into the critical section, not a more than one process. But if I am making semaphore value is a positive, then your critical section, according to the process synchronization rules, mutual exclusion is failed. This is the only one case counting semaphore becomes what? Unuseful one. But rest of the case is a wonderful counting semaphore. So what is a counting semaphore? We will see it. So counting semaphore, the value of the semaphore can be incremented, can be decremented as many number of times, we don't mind. But it is maintaining the modified structure of semaphore because it has to avoid the concept of spin lock and busy waiting. So what is a new modified structure? Observe carefully. Up is nothing but signal function only. So up semaphore, s dot value is equal to s dot value plus 1. After incrementing, you observe if s dot value is still lesser than is equal to 0, which indicates that what? Less than is equal to 0 means some process already in suspended list. So we have to wake up them one by one, one by one. So select a process from the suspended list and give a wake up system call. This is a signal function. What is down? So s dot value is equal to s dot value minus 1. Successful down means value will never become a what? Negative. If it is unsuccessful down means value becomes a negative. So s dot value is less than 0, then it is unsuccessful down. Therefore, you need to send the process to suspended list and raise a sleep system call. This is a counting semaphore concept. Let us go for one small example. Semaphore value is equal to 1. Then when a process P naught, now which semaphore I am using? There is a name for this. That is nothing but counting semaphore I am using. Counting semaphore avoids busy wait concept. Remember this. It's not a normal semaphore. So P naught is checking whether he can able to enter into critical section or not by asking wait function first followed by signal function. What is the wait function? Let us see. S dot value is equal to S dot value minus 1. Okay. Then it becomes how much? Already your initial value of semaphore is a 1. Counting semaphore 1 becomes a 0. Now it is checking a condition if S dot value less than 0, then suspend and give a sleep system call. In this case, it is not less than 0. Therefore, P naught is entered into a critical section happily. Okay, one more process has come now. Already P naught is in critical section. P1 is trying once again. Wait function. So P naught is giving here wait function. Here P1 is giving a wait function. It also wants to access. S dot value is equal to S dot value minus 1. What is the latest S dot value? 0. Then 0 becomes minus 1. We will check the condition if S dot value less than 0. Is it less than 0? Yes, it is true. When it is true, then you raise a sleep system call. Now, in the suspended list, if you observe, this is your suspended list. If you observe that, there is a process P1 inside. Whoever comes, even P2 comes, P2 also suspended. Even P3 comes, P3 also suspended. For P1, what is the semaphore value? It's a -1. For P2, what is the semaphore value? It's a -2. For P3, what is the semaphore value? It's a -3. -3 indicates 3 processes in suspended state. +3 indicates 3 process can enter into critical section. 0 indicates some process already is in critical section. So 3 important terms with the counting semaphore. Positive, those many number of process can enter into critical section, which leads to mutual exclusion property. And negative, -n, which indicates that those many processes are in the suspended list. If S value is equal to 0, critical section is busy, somebody is already inside because it is locked. So who has to give a wake up call? Whoever is in the critical section. P naught is responsible for give a wake up call. Now, after some time, this guy is under suspended. Then after some time, because this guy is initiated, after wait, P naught is issuing a signal. When P naught is issuing a signal, then what is the function of signal? S dot value is equal to S dot value plus 1. S dot value is equal to S dot value plus 1. So 0. What is S dot value right now? If it is -3, then -3 plus 1, which is nothing but -2. -2 indicates that 2 processes are in suspended list. Then after that, it gives a which system call? Wake up. Then it brings this process P1. Then P1 can successfully go for wait function and can access what? Critical section. This is how send the process to suspended list, bring the process from suspended list to CPU. That means to access what? Process the critical section to satisfy process synchronization rules. So when S is equal to 1, no problem. P naught is asking for wait of yes. Then 1 becomes 0. P is under critical section. Then after that P1 is asking for wait of yes. It is not possible because 0 becomes -1. And P1 is under suspended according to piece of code. P2 also come, wait of yes, -1 becomes -2, it is also suspended. And P3 also come, it becomes -1, -2, -3, it's also suspended. Then while he is going back, he has to issue signal. When he has given a signal, because right now P0 is in critical section, when he has given a signal, then the latest semaphore value becomes -3. Observe, S is equal to -3. When he becomes a signal, then -3 plus 1 becomes a -2. Then P1 is entering into the critical section because it has given a wake up system call. See the code. What is the code? S dot value is equal to S dot plus 1. If S dot value is still lesser than is equal to 0, select a process from suspended list and wake up. So in this case, the P1 raised and enter into critical section. Then when P1 is going back, again you will issue signal. Then your -2 plus 1 becomes a -1. This time P2 is inside critical section. Then once the P2 is also completed, then the P3 is coming. This time -1 plus 1 becomes a 0. Then process 3 also can enter into critical section. And while leaving, P3 has to give a signal. Then 0 becomes a what? Plus 1. Again it is set to S is equal to 1 value. So every process, while entering into critical section, give a wait. If a wait is successful, you access the critical section. If wait is unsuccessful, you be in the suspended list. And the process which is already in critical section is responsible to give a signal call. Then the signal is going to cross check after applying a plus value. whether any processes are inside the critical section or not, sorry, inside the suspended list or not. If any process is inside the suspended list, then immediately you wake up, and every process is responsible to wake up other suspended list jobs. So operations on counting semaphore, down and up, which I already told you. Down means a -1, up means a +1. Any number of downs you can do, any number of ones you can do, ups you can do. So after performing down, if the process is getting blocked or suspended, then it is known as unsuccessful down. This is very, very important point. If it is a negative value, then that particular process, whoever attempted for wait, becomes a what? Suspended job. So unsuccessful down will not continue the execution. Process enter into the suspended list, and the down on the counting semaphore unsuccessful as long as the value of S is what? Less than 0. After performing a down, if the process is not getting blocked, then it is called a successful down. If it is successful down, then the process will continue the execution. The down on the counting semaphore is successful only when the semaphore value greater than is equal to what? 1. So successful down and unsuccessful downs. Unsuccessful downs mean the processes will be in suspended list. Successful down mean the processes are entering into critical section, and S is equal to 0 means one process is already inside the critical section. This is up. There is no unsuccessful up. It's always successful only. +1, +1, +1. The process is performing off will definitely continue the execution. If the semaphore is a +6, which indicates that 6 process can enter into critical section, that means 6 successful downs. 6 -1, 5 -1, 4 -1, 3 -1, 2 -1, and 1 -1 till you reach to 0. So if it is a -6 means 6 suspended process. So S is equal to 0 means some process is already inside the critical section. S less than 0 means those many process are in suspended list. And S greater than 1 means those many processes can enter into critical section by making successful downs. Yeah, this is a very, very important question for a GATE campus placements. So it said that at a particular time of computation, the value of semaphore is equal to G7. Semaphore value is 7. 20p. P operations are how many? 20. P means what? Down. Minus 20. And 15 V operations. P is nothing but wait. And 15V. V is nothing but signal. So signal how many? 15. So the result of the value of the semaphore is finally how much? So 7 plus 15, it is 22. Minus 20, it is 2. The final semaphore value after doing this discussion is becomes what? 2. The meaning of 2 is nothing but 2 process still can enter into critical section. What is the meaning of minus 20? Minus 20 are already 20 process already in suspended list. This is another question. So semaphore value initially 10. 6 wait. 6 wait means minus. Balance is 4. 4 signal. Signal means plus. So your semaphore value is equal to 8. This is a wait function minus signal function plus. What is the meaning of 8? 8 process can enter into critical section successfully or 8 successful downs. So the advantage of counting semaphore is wonderful, but only one problem. That is what? If at all S value is greater than 1, those many processes can enter into critical section, which leads to failure of mutual exclusion. So this problem can be eliminated using binary semaphore. The operating system uses right now binary semaphore only. Binary semaphore sometimes also called as a mutual exclusion because it has got only two values. One is a 1, the other one 0. That's why it becomes a binary 0 or 1. 1 indicates that available, 0 indicates that unavailable. If at all semaphore value becomes a 0, then you will be suspended. If at all semaphore value becomes a 1, then you will be granted to access critical section. So by default satisfies mutual exclusion property. A binary semaphore can be used as a mutex, but a mutex can never be used as a semaphore. So what is the structure? So you're having a values, two values 0, 1 enumeration values, and a queue consists of list of the processes which are under suspended. So what is the piece of code? Let us see. Up function and down function. Up is nothing but signal, down is nothing but wait. So up function we talk. If suspended list is empty, then s dot value is equal to 1. Else, select a process from suspended list, then give a wake up call. Down function. If s dot value is equal to 1, then s dot value becomes 0. Otherwise, suspend a process. Okay, let us see an example. So there are few processes by name P0, P1 and P2. They are fighting for critical section. So first of all, they have to go for wait of your binary semaphore. This time, the name of the binary semaphore is yes, I am taking. You can keep a mutex, I don't mind, but I am taking regular name yes. Let initial value of s is equal to 1. So this time, how binary semaphore works? When I say wait of yes, it cross-check me. Wait of s means down function. If s dot value is equal to 1, yes, it is a 1, then s dot value becomes 0. Yes. Then you are entering the critical section. Then while leaving back, I am using signal of yes. Let us read signal code. What is a signal code? If s dot list is empty, yes, suspended list is empty. Nobody is there in the suspended list. Observe. Nobody is there in the suspended list. Therefore, if s dot list is empty, then s dot value is equal to 1. So 0 becomes 1. Okay, in the same way, wait of yes, successful 1 becomes 0. In the same way, signal of yes, 0 becomes 1. Now, I will show you different example. Let us say binary semaphore I am using s is equal to 1. Now, process naught and process 1 is fighting for the resource, and it is saying first of all, as usually, wait of yes. What is the condition? Down function. What is the down function? See the code of down function. If s dot value is equal to 1, yes, it is equal to 1, then s dot value becomes 0. Now preemption came. P1 preempt P0. P0. And what happened? P1 got a chance. Now P1 is trying at his side. Wait of yes. What is the wait function? Let us go back. What is the wait function? Down. If s dot value is equal to 1, no. S dot value is not is equal to 1. S dot value is now how much? 0. Now immediately it will send you to where? Block the process and make a sleep. Block the process. Whoever processes are coming now, even P2 or P3, they're supposed to be under block because somebody is already inside the critical section according to binary semaphore code. Then who is responsible to wake up? P0. Whoever is inside the critical section is issuing signal S. So what is the signal S? Now observe carefully. Signal S is nothing but up. It is checking. S dot list is empty? Not at all, because your S dot list consists of two processes inside the suspended list, name P1 and P2. So you are having a two processes in a suspended list. Then your condition becomes what? Your condition becomes S dot list is empty? No. Your condition becomes false. Then it goes to else. Select a process from suspended list and wake up. So select a process from suspended list and wake up. Now P1 got a chance. Again while P1 is releasing critical section, again signal of yes. What is the signal of yes? Again it will cross check. S dot list is empty? Not at all. Again it has given a chance to P2 this time, and while going P2, he has to give a signal now. While signal, again it cross-checked. We see P1 is removed and P2 is removed. Now suspended list becomes empty. Now P2 is cross-checking. S dot list is empty. Yes. Then it put S dot value is equal to 1. Now it reset the value of S is equal to 1. This is how to wake up and how to sleep the processors using binary semaphore. So the advantage of counting semaphore is binary semaphore is by default it is satisfying mutual exclusion, and disadvantage is cannot handle bounded weight as it is just like a variable that binary value hold binary value. So what is the advantage of binary semaphore? The advantage of binary semaphore is it by default provides what? Mutual exclusion. So these two solutions, counting semaphore and binary semaphore, avoids busy waiting concept. So that's why your semaphore structure is modified by adding a one more field called a suspended list. But counting semaphore acts differently, binary semaphore acts differently, wait function and signal function. The differences, binary will give mutual exclusion, value is 0 and 1, only one slot, cannot guarantee bounded waiting. Counting semaphore may or may not give mutual exclusion because if semaphore value may be greater than 1, an integer value with a more than one slot and provides a set of processes. And there are other two terminologies like a strong semaphore and weak semaphore. What is the meaning of that? As we have seen, suspended list. As we have seen, suspended list of the process. Let us say there are three processes are suspended because critical section consists P naught. As P naught is going out of the critical section, he has to issue signal. When he issues signal, he has to pick some process from suspended list. Which process I need to pick? Which process I need to pick from suspended list? Therefore, fairness is maintaining. That's the main concept of strong. If you are using a strong semaphore, it checks the order which process is first enter into suspended list and next and next. First arrival process to the suspended list will be brought back using a wake up system call. In this case, P1 will first wake up, then P2 will wake up, then P3 will wake up. If you follow that order, it is a strong semaphore. If you not follow that order and you are taking on its own, it is called as what? Weak semaphore. So this is about strong semaphore, weak semaphore, counting semaphore, and binary semaphore. So these two semaphores, counting and binary semaphores, are real-time implemented because we want to avoid the concept of busy waiting and the concept of spin locks.